Hey guys, we are going to take a couple of minutes and talk about the first half of chapter 13. Yeah, last chapter. And it is all about thermochemistry. And thermochemistry is defined as the study of heat that is absorbed or released by chemical processes. So in order to understand thermochemistry, you have to understand what energy is and what is energy. Energy is the ability to do work. Okay, so then what is work? So work is the application of a force to move an object over a distance. So if we combine those definitions, what we learn is that basically energy is the ability to cause motion. Now here's the crux of the matter for any chemical process. When matter is involved in a chemical process, there's always a release or an intake of energy. Okay, so and that often happens through heat. Now, what is heat? So heat is energy that is it's transferred from one substance or one medium to another because of the difference in temperature or a change in phase. Okay, so heat has to do with energy, but is heat, yes, heat has to do with energy, has to do with the change in temperature, but is temperature a direct measurement of heat? It turns out that it is not. It is an indirect measurement of heat. Why do I say that? So, what temperature tells us is the amount of expansion that occurs in a liquid when heat is applied to a liquid. So what we are doing, if we are measuring the temperature of something, is we have an indirect measurement. So we are measuring the effects of heat on a substance, but we are not measuring heat itself. Okay, so while there is a relationship between a temperature change and a change in energy, they are not the same. It's an indirect measurement that corresponds, but it's not exactly the same. So there are two particular units we use to measure energy. One is the joule, okay, and one is the calorie. And the calorie is defined as the amount of heat that's required to raise 1 gram of water 1 degree Celsius. Okay, we also know that 1 calorie equals 4.184 joules, and you saw that in your book. It's not an exact measurement, so you do need to count sig figs whenever you're using a conversion from calories to joules. So that is how yes, calories, the amount of heat required to raise 1 gram of water 1 degree Celsius. That's a calorie. Now it turns out that every material has its own innate ability actually not an innate ability. It has a specific amount of heat it requires, amount of energy it requires to raise the temperature of that substance. Okay, so we have this term called specific heat capacity, which is the amount of energy that's required to raise the temperature of 1 gram of any substance 1 degree Celsius. Okay, so obviously when we're talking about the calorie, we're talking about the specific heat of water, right? Yeah. Okay, so, but to think about this, to help kind of clarify this concept in your mind a little bit, if you are burning 2 different masses, okay, so let's say we have 50 grams of paper and we have 50 grams of steel. Which one is going to be easier to burn? Obviously, paper is going to be easier to burn because it has a lower specific heat. It takes less energy to raise its temperature, right? Whereas steel would take more energy. So every substance has its own specific heat, the amount of energy it takes to raise and heat that thing up, okay? It also turns out that when we're talking about the heat that's involved, the energy involved with temperature changes, we have to look at the masses of things. Because if let's say I have a log, right? And if I have a stump of a tree that I'm trying to burn, okay? And it would take a certain amount of energy, right? It would take a lot of energy. If I was burning a branch from the same exact tree, same exact substance, but it has less mass, it would obviously take less heat or less energy, to burn that thing. So not only is our energy changes related to the actual substance, but they're related to the amount of the substance that you are changing the temperature of or applying heat to. Okay, so it turns out that we have a mathematical equation, of course we do, that allows us to quantify the change in temperature, okay? And the equation that you have is delta T equals Q over M times C. What do those all mean? Okay, delta T means change in temperature. So for those of you that are going into physics next year, you're going to get really comfortable with delta quantities, Okay, whenever you see a delta quantity, it means the final quantity minus the initial quantity. So if we have a delta T, that's the final temperature minus the initial temperature, and that equals Q, which is our change in energy, divided by the mass times C, and C is our specific heat of that particular object, okay? So you're gonna get really good at that equation in this particular chapter. Oftentimes, the way we will see that equation is that Q, the energy change, equals M times C times delta T. All right, so MC delta T equals Q, and that gives us the energy change. Now, it also turns out that when we quantify the energy change, we have to quantify whether it's being released or whether it's being absorbed. Those are our two options. Either energy is going to be released by an object, or energy is going to be released, or absorbed. Those are your only options. Okay, so when we talk about heat being released, let me get my thing here real quick. Make sure I'm heading down the right path. Oop, I don't know where it went. When we talk about heat being released, we're going to quantify that as a negative number. It's not that it's actually negative, it's not right, but we have to be able to distinguish, is that object releasing energy or gaining energy, okay? So when we talk about releasing energy, we're gonna just quantify that as a negative quantity. And when we absorb energy, we're gonna talk about that as a positive change in energy, or positive Q, okay? And that leads me to this idea of calorimetry. So calorimetry is one way that we can measure changes in energy. And I'm just gonna explain it really quick, and then that's it for today. So a calorimeter is an insulated object that you put a mass of water in, okay? So then what you do is you heat up an object that you're trying to determine, well, you can figure lots of different things out, but you can heat that object up and get it to where it's a known temperature. Typically, we're gonna take it to boiling, because we know if it's boiling, right, and it's been in boiling water for 5 minutes, then it's gonna be at the same temperature as the water, which means it's gonna be 100 degrees Celsius, right? And we're also going to measure the mass of our water inside the calorimeter, which is basically like an insulated cup kind of thing. And then we're going to measure the mass of the water in there, and we're going to measure the temperature of the water in there, okay, it's going to be at room temperature. So then we're going to take our very, very hot object, and we're going to drop it into the calorimeter, okay? Now, what happens? Well, obviously, the very hot object is going to release energy, and energy always goes from warm to cold. So the object that's hot, that's 100 degrees Celsius, is going to cool off by releasing its energy into the water, which is cooler. So the overall temperature of the water will come up, and the overall temperature of the object will go down. And what you do in a calorimetry experiment is you would record the temperature every 30 seconds for 2-3 minutes. And what you'll see is the temperature will rise by a degree or two. It's not typically a huge change unless you have a very, very heavy object. But then when it stops is when the temperature stops changing, or if the temperature were to dip down a little tiny bit, that would actually tell you then that it's some of the temperature is going back to the object, right? So that's how you do a calorimetry experiment. And what you learn by that is you can learn, a lot of times you can determine what the object is, right? Because if you can solve for that C variable, the specific heat, then you can look up and see what object has that specific heat, because every substance has its own specific heat. So that's kind of why you do calorimetry, and we'll do several problems, work through it. I have a sheet and an example problem for you to watch if you want to, but that is the beginning and the kind of the nuts and bolts of heat and thermochemistry. There you go. Thanks, guys.